Buenos dias, muchachas y muchachos, and welcome to another edition of Finzics. It's Mr. Finn coming to you from neighborly Northville here and trying to reach you today. It's the day of our Google form on statics and fields. So what I'm going to do, guys, I'm going to forego the introduction to parallel circuits and move that to Monday. So today we can just focus on the review for the larger Google form. It's going to replace the event that we would have had on March 17th for chapters 32 and 33. Okay, so again, Google form today between 3 and 6 p.m. That is the first order of business. And the introduction to parallel circuits, Monday, April 13th, when we come back from Easter weekend. Okay, guys, so real quick, I don't want to spend too much time on it. Treat this kind of like a test day, because you guys do have the Google form later. But I did bring my electroscope back over today to just review statics in general. You guys remember that friction was a way of building charge. I've got my balloon here, and I've got some fur. So if I rub it, I can get a balloon to charge up, and then I can bring it close, and of course I can polarize the electroscope. Meaning, if I bring a charged object close, the needle deflects, but this scope is not charged because when I take away the charge, this thing goes back to zero. So electrons on the front of this balloon are coming close to the electrons in the ball. Because this is a conductor, electrons are free to move down into the bar. Now, why do they go into the bar? It's lightweight. Electrons can spread out and get away from the frame. So this represents a way that electron repulsion could give you a better value of stability, more stable format. Now, what would happen if we actually touched it? Okay, so if we touch it, then you can see, oh, let's see, it didn't work there. Let's see if we can touch it. Charged object. There we go. Now, when we touch it with a charged object, that's the second way of charging an object, and that's conduction. If you guys remember, conduction happened between two surfaces touched. One of them was charged, and the other was not charged. But when they touch, electrons move from the charged object to the uncharged object. Now, we didn't get into how much charge moves. That's a little bit more complicated. We actually have to think about something called charge density, and the charge density would be equal between those two objects, but we're not going to talk too much about that. Now you can see that I touch the balloon to the scope, and the needle remains deflected even when I take away the balloon. Sure, the balloon still had some charge on it, but some of the charge moved to the scope until the scope remains charged because the needle remains deflected. That's called conduction. Remember, the process of grounding occurs when an infinite reservoir of neutral charge is used, either to supply electrons or we can deposit them there. So I'm acting as the ground for this device. I am an infinite reservoir of both millions and millions of protons and millions of electrons, so a few extra electrons into me makes no big deal. But a few extra electrons here with its small area makes a much bigger deal. Now, the harder one was induction. Remember when I charge this, put my finger on one side, bring in the balloon, and I take away my finger. And you can see that the needle remains deflected. Now, if this was a negatively charged scope, and I brought a negatively charged balloon close to it, it would further deflect because electrons would still run away from the negative charge into the bar and further deflect. But as I bring my balloon in here, the needle goes back to a more neutral position. So that must mean that in the current state, this electroscope is oppositely charged from this balloon. Again, I bring the balloon in, and the needle goes back to a more neutral position. I take away the balloon, and the needle comes back out. That means that this electroscope is oppositely charged from this balloon. And I charge the balloon negatively. Therefore, this electroscope must be positive. Now remember guys, that's charged by induction, where I didn't actually touch the charged object to the device that I was charging, but I did use my finger and I used ground as a way of doing that. So charging by induction involves polarization. I gotta have polarization, but it can include ground or it may not include ground depending on what you do. If you guys remember the two spheres that were together and the charged object came close to the two spheres and we separated the spheres. Well, there was no grounding going on, but we separated the spheres while they were polarized. If you don't remember that, please look at the video by Crash Course Physics on charge and electric fields. That's a great review. And they do talk about both grounding and not grounding as a way of being involved in the charge by induction. So three ways, guys: friction, conduction, induction. Again, when I ground, I go back to 0. And that's it for charging. Now, what else? Well, remember we talked about the electric fields. We talked about electric fields. We talked about Coulomb's law. We talked about the Van de Graaff generator and how it works. Remember the Van de Graaff generator video. Now, I don't have access to that, but if you guys Google the Van de Graaff generator, you can get a pretty good array of demonstrations by the Van de Graaff generator. Faraday's law. Remember, that's where a shield could be placed. If I placed a shield around this charged object, I can deposit charge on the inside, but I can't get charge back. The electric field remains 0 within a caged or enclosed loop. So remember, there are a few videos on that with the trash can and the radio and a few other things. So please review that through chapters 32 and 33. Let's go to the magic board again now, just to recap some of those concepts so you guys can refresh them. Okay guys, we're back. Let's take a look at some of the concepts that we're reviewing for today's Google form. The first is Coulomb's law. The electric force is dependent on K, the electric constant of the universe, which is 9 times 10 to the 9th, times Q1, Q2 over D squared, where Q1 and Q2 are charges, any charges we want, and D is the distance between them. Or you may see R there. Remember, the D or the R is squared in the denominator. So if you guys are looking at something like that, make sure you get the fact that D is squared in the denominator. Because that's where a lot of kids make mistakes. Electric fields. Remember we talked about the electric fields, both in between point charges with our electrodes in the oil solution with grass seeds to see the electric field lines for the first time. And remember, electric fields are used to store energy. We can do so in things called capacitors. Capacitors store electrons in electric field. They store energy in electric field for later use. So we can use that to smooth the flow of charge with a diode, or we can just use it to store charge in general. Electric fields are given by force divided by charge, which is expressed in newtons per coulomb, mostly. Voltage, the definition of voltage came out in chapter 33 too. That's electric potential energy per charge. Now remember, electric potential is not the same thing as electric potential energy. Electric potential is another name for voltage. But electric potential energy is simply the potential energy in electric form. Kind of like PE's of gravity, potential energy gravitational, or PE elastic, like the elastic potential energy of a rubber band. There's all kinds of potential energy. This just happens to be the electric kind. And if we divide that potential energy by the value of the charge, we get the term voltage. Current. Remember, current is the flow of the charge per time. So the amount of coulombs or electric energy that flows through any area in a given amount of time is called current. We measure that in amps. Faraday's law, that's what I just discussed a moment ago, where the electric field inside any closed conductor has to be 0. No matter how much charge we deposit inside the closed conductor, the charge never remains there. It moves to the outside due to something called electrostatic equilibrium. Once again, guys, if you need more on that, check out that great video. It's about 10 minutes long by Crash Course Physics, where she addresses almost every single one of these topics. Okay? All right, guys, let's wrap up. Okay, guys, that just about does it for the wrap up on statics and fields. Hope you guys can do a little bit of studying today and maybe review some of your homework questions for the Google form today. One more quick announcement. The district did come out with a continuous learning plan for the rest of the school year, and we're supposed to do some planning with our fellow teachers from April 13th to April 15th. And they're going to try to roll out that plan on April 16th. Well, you guys know that I've been doing my thing consistently every day. But if we do get a day or two where there's no video, I'll make sure I put an announcement out in the classroom, and I'll also update the Google Doc to reflect that. I may need to do some planning with my other physics teachers to figure out any additional resources we might be able to use to help you guys along. But other than that, keep up with the stream, guys. And I know you're doing a great job. The stuff I've been receiving since we've been away from school has been really good stuff. So let's keep it up. Let's have a great end of the school year. And if there's anything you need me to address that I have not addressed on these videos, please send me an email and I'll make sure I do that. Okay, guys, good luck today and have a great weekend. And we'll see you after the holiday.